Hi guys, so I usually spend a fair bit of time putting a video like this together, but given the current situation with school closing, I'm just trying to get this out to you as quickly as I can. So the point of the video is just to help you understand the C5 chemical change topic. I know it can be hard to learn at home on your own and not have your questions answered, so if you want to drop me an email or put a comment on show my homework, then I can get back to you and help you with whatever it is you're struggling with. So pretty much this whole topic is looking at reactions of metals and reactions that make salts. So I'm going to make two videos, one for reactions of metals and one for making salts. So initially we need to look at how we get metals. So metals can be extracted from their ore. So this is when a metal is combined with a rock. So you will have looked at this idea in year 9, and an example that you might remember is malachite. So this is a slightly bluey green rock that you can get copper out of. So when you want to extract a metal, it's important to know how reactive it is. This is because you could extract it by displacing it, which is when you use a more reactive metal to get it out. But I'll explain a little bit more about displacement later. So a metal could be removed using reduction. So this would be a process where oxygen is removed. So if during extraction process a metal has reacted with oxygen, we would call this an oxide. So using our copper example, it could be found as a copper carbonate. We would then heat it up until it breaks apart. This is called thermal decomposition. It would form copper oxide, and it would also give off CO2, so carbon dioxide. Because the metal is then an oxide, we could reduce it using carbon or using hydrogen. So reducing can mean a few things, but here it means getting rid of the oxygen. So heating the copper oxide with carbon would give us copper and CO2. See here, the carbon has reacted with the oxygen and formed carbon dioxide. So our other option is to heat the copper oxide with hydrogen. So this would give us copper and water, which would be in the form of steam because we've been heating it up. So earlier I told you that metals reactivity can help us decide how it should be extracted. So in previous years, students were given the reactivity series in the exam to help them. Unfortunately for you guys, you now have to remember it on your own. So we use a mnemonic to help you remember this, and it just shows you the order in which they go. I've added the word cute into it, so cute zebras, because carbon should be in there too. So you can probably see that hydrogen is in there as well. It's our other non-metal, but they're both included within the reactivity series because they can both be used in metal extraction. It can be a little bit tricky to remember which metal goes where, especially because some of them start with the same letter. So you've got lithium and lead there. And you've also got calcium, carbon and copper. I remember this by thinking about it in alphabetical order. So calcium would come first, so Cal would come before Car for carbon, and finally the Co for copper. So if that helps you, great, but otherwise anything that you can think of to help it stick is fantastic. So in the exam, they might ask you to describe a reaction between metals and water or metals and acid. So knowing the reactivity series can help you to suggest what the reaction would look like. So most metals you've come across wouldn't react very much with water. So you'd be saying things like a very slow reaction or very little or no reaction. However, there are three metals that three metals that you look at that when added to water have a huge reaction, and they're all found in group 1 of the periodic table. When we're back at school, I'll do this as a demo to help you remember it for the exam, but basically you need to know that as we go down the group, the reactions get more extreme because the reaction gives off more hydrogen more quickly. So here's a video link, but if you type into Google group 1 metals in water, and then you can add the word brainiac if you want to, but it should come up pretty quickly. It's a really dramatised version, so don't expect that level of reaction when I demonstrate it. But you need to know that when these metals react with water, they make an alkaline solution. So if we were to add universal indicator, it would go a bluey purple. So that's where they get their name from, they're alkaline metals. If this is how they react in water, you probably wouldn't be surprised to hear that if you add them to acid, there'd be an explosion. Then as you go down the reactivity series, the metals react less and less. So I've just provided a table here to show you what you'd expect to see if you observed one of these reactions. Okay, and the very last thing we need to go over in this video is displacement. So displacement means to move something from its place. An example of this could be talking about the movement of people after a natural disaster or maybe war. So you could say that the community were displaced. But in chemistry, we're talking about moving an element from its place. And in this case, we're talking about metals. The definition you need to know is displacement is when a more reactive metal displaces a less reactive metal from a solution of its salts. So basically what we're saying here is the more reactive metal kicks out the less reactive metal. So a good analogy of this is thinking of the more reactive metal as a bully, and then the less reactive metal is a little bit of a weakling. So the less reactive metal is hanging out with his little friend, the salt solution, and the bully comes along and kicks out the less reactive metal and hangs out with the salt solution herself. So she goes off with the salt solution and the weak, less reactive metal is left on his own. So let's put that into a chemistry example. So I've chosen zinc as our more reactive metal. You can see that in the reactivity series. So I've selected iron as the other one, so that's a less reactive metal. And the salt solution is sulfate in this case. So we can see that in the course of the reaction, zinc kicks out iron and stays with the sulfate, and iron is sat on his own. So everything that we started with is still there at the end, nothing is gained and nothing is lost. Okay, so that's the end of this video. I'm going to make another video for the salt making, so watch out for that one.